Okay, so it is first of all, hello everyone. It is my great pleasure to welcome Andy Shepherd, for this third game changer online lecture in Earth observation. So I will briefly present you, Andy. So you are professor of Earth observation at the University of Leeds in the UK, and you are also director of the NERC Center for Polar Observation and Modeling. So for your research, you use satellite observation to study the physical processes occurring in the climate system. And your most renowned contribution, I would say, consists in measuring ice mass loss from the Antarctic and Greenland ice sheets using different space systems, in particular radar interferometry and radar altimetry. And with the objective to quantify their impact on sea level rise, and more generally to understand their interaction, the interaction of the ice sheets with the global climate system. You are also deeply involved in the calibration and validation of the satellite system, and you have been leading field campaigns in Europe, Africa, Greenland, Antarctica, and certainly elsewhere to calibrate and validate the satellite missions. You are also interested in the development of novel satellite sensors for various applications in geoscience. And in that context, you work closely with technical experts of space agencies, in particular the European space agencies, and with also the space industrial sector. But you also work with the scientific community, obviously, in glaciology, meteorology, oceanography, etc., and with government agencies. You are currently the principal scientific advisor to the European Space Agency CryoSat satellite mission, which is the topic of your lecture today, and co-leader of the NASA ice sheet mass balance intercomparison exercise. You have published more than 100 peer-reviewed papers that are often reported in the media, and you regularly contribute to broadcast documentaries, in particular with the BBC in the UK. So you have been awarded several prizes. Let's quote two: the Philip Lever-Ulm Prize in 2008, and the Royal Society Wolfson Research Merit Award in 2014. So now the floor is up to you, and we are listening to your presentation for 45 minutes.
Okay, well, thank you very much, Annie and Co, for inviting me to give this presentation. I'll try to get through all of the slides. I've written it this week, so I really appreciate the opportunity to refresh the content on CryoSat. It's really not just my own work, it's lots and lots of other people's work, and I'll try to credit people as I go through. If I run out of time, I'll skip some slides towards the end, because that's less about the satellite observations and more about what the impacts of the signals that we've seen are for us. But I'll make sure that the presentation is available in case anybody wants to see those slides, just in case I missed them. So I'll talk about CryoSat and really what we've learned from a decade of polar altimetry. We didn't really have that capability before the mission was launched. In particular, this talk is a contribution from several of the people I've worked with over the past 10 or 20 years. My PhD students over the years in particular, but also colleagues at the European Space Agency, Rob Cullen, Marcus Engdahl, Richard Francis, and Tommaso Parinello. And also a lot of the graphics that you'll see today are produced by Philip Eales at Planetary Visions, and we've worked with him for many years now to try and improve the way we can communicate our results. And so hopefully you'll like some of the things that we've seen, we're about to show you. And of course, my colleague, long-term colleague, Duncan Wingham, who's the CryoSat inventor, and he's now at the Natural Environment Research Council. So I need to credit my PhD students because all of the work has involved them to one degree or another, and they're still active in science, and you'll know many of them. Many of the people on the call will know these people. They've all contributed hugely to the different results that I'll present today on either sea ice or land ice, mountain glaciers or ice sheets, ice shelves, the southern hemisphere or the northern hemisphere. They've worked on all of the different subjects, and I wouldn't be able to show the results that I'll show today if it weren't for their contribution. But in particular, I also want to thank the many other people that have worked on CryoSat over the years, because as Principal Science Advisor, I'm really grateful for other people making use of the mission data as well. What I'll say is that most of the illustrations in this presentation, because they're post-processed and polished, they derive from our group, but there are many different flavors of results from the other groups around the world, and I'll try to credit people along the way. And I apologize for not showing your slides. It's just a case of not having the content to show in the presentation. So I'll talk about ice and climate really briefly, first of all, about why we should care. Quickly about CryoSat 2, in case there are any people on the call who are not familiar with the satellite. Then I'll give some examples of polar science that we've managed to illuminate with CryoSat measurements. I'll try to talk about Earth's ice imbalance, which is a result that we've recently published, which brings together lots and lots of different CryoSat measurements. I'll talk about some impacts of ice loss, and actually one of the things that I try to add to all of my presentations these days, because after 30 years of developing satellite measurements of the polar regions, the story is pretty bleak, actually, for most people, and it can be very difficult to detach yourself from the reality that the signals that we're seeing are not helpful for people around the world. And there are still questions as to what we can do to help, and I'll try and touch on that later on. So the reason that we're interested in the polar regions is because they play an important role in the climate system. And if you want to learn about that, there are lots and lots of different ways you could do that. But for instance, play this video game that Anne LeBrock made, Ice Flows, and you can play with the glacier system, and you can change the amount of snowfall or ocean melting or surface melting that occurs to that glacier. You can see whether it grows or shrinks. There's points to be gained. It's meant for school kids. But the basic principle is that if it snows a lot, then ice will grow. And if it melts a lot, then the ice will shrink. And we monitor the ice and try to understand whether or not it is snowing too much, snowing too little, melting too much, or melting too little. And that's really the job that we've been doing for 10 years with CryoSat, and a bit longer with the other satellite missions that ESA have produced. In the Northern Hemisphere, in particular, we've seen really strong signals of sea ice retreat, and everybody will be familiar with that. But CryoSat plays a really important role here as well, because although we've had 30 to 40 years of measurements of sea ice extent, and how that's changed over the time, sea ice is mobile, and what matters is how much there is, not just how evenly it is spread across the Arctic and the Southern Oceans. And so we need to know how thick it is as well, and CryoSat provides a method for getting at that particular number from space as well. And it's really important to have measurements from space, because the polar regions are inaccessible, except in places like this. This is Prince Gustav Channel in Antarctica, and it's now accessible because an ice shelf that was formerly there and had been for the entire Holocene period collapsed in the 1980s. And so Greenpeace and other tourist ships can sail through Prince Gustav Channel now in a way that you couldn't do even in the 1980s. And this is a signal of climate change that has really been one of the iconic events in my lifetime, at least, because it's been really abrupt, and we've learned quite a lot about the climate system since then. So this is the former Prince Gustav Channel ice shelf. It was between the mainland Antarctic Peninsula and Ross Island, and it's the seaward extension of a glacier flowing out into the ocean and spreading out and hitting this from left to right here, hitting Ross Island and staying intact, but still floating on the ocean surface. And we used to think that ice shelves didn't really matter too much because we thought the glaciers that were behind them were insulated from changes that might happen in this part of the climate system. But it's actually not true. So if I show a time sequence of satellite images for the Larsen ice shelf and the other ice shelves at the northern Antarctic Peninsula, you can see what's happened since the mid-1980s. Progressively, huge chunks of ice, the size of London or Paris or another big major city, have broken away and drifted off into the ocean. And they haven't been replaced because it would take about 1,000 years to replace these pieces of ice. But you can learn about why they might have broken away and how important it is in different ways. If you sail a ship, and people did this, Jean Domack and Carol Pudsey, among others, sailed a ship into the embayment after the ice shelf had gone and collected sediment core samples from the seabed and analysed those sediment cores for microbial deposits and other things, dated them, and inferred that the ice shelf had been present for 10,000 years. They could tell that because these sorts of organisms like to live in the light and other ones like to live in the dark. And looking at their abundance throughout the sediment core record, you can map through time when the ice shelves were present. So this is a real abrupt event, and it's happened in our lifetime, and there are no greater abrupt events in the climate system than ice shelf collapse. The question as to whether it's important is easily addressed if you just fly over one of the glaciers today. You'll see these, they're trim lines. This is where the glacier used to be when it was thicker and moving more slowly than it is today. When the ice shelves collapsed, these glaciers speeded up by a factor 5 to 10 in places, and they're now pouring more ice into the ocean. So ice shelves do matter, and abrupt climate change signals do happen. This is Drygalski Glacier, mapped from space, speeded up by a factor 6 since the ice shelf collapsed. So does it matter if ice is out of balance? Well, this is a schematic, shows the size of the polar ice sheets relative to where I live in the UK. You can do this for any country. They're really big. They need to be monitored by satellites, and they're a potential threat to our sea levels because Greenland contains about 7 meters of sea level potential, and Antarctica something like 60 meters, 55 to 60 meters potential. And of course, we wouldn't want to lose that amount of ice anytime soon. We've relied upon model predictions. This is a prediction from the 5th assessment report of the IPCC under recommended concentration pathway 8.5. So this is an extreme warming scenario. And at that time, the sea level contribution due to Antarctica and Greenland in the future wasn't expected to be very high, maybe a 10 centimeter change over the next century. And so we see these changes in the cryosphere, and the question still remains to be answered of whether or not they're important, whether they'll be a concern for us in the future. Because we know when we look at the climate system, it's responding in ways that the models that go into these climate projections don't reproduce. So we have several key processes for land ice in particular here that are not really included in the model predictions. Lubrication of the glaciers as the surface melts, that's a feedback loop. Carving and breakup of ice shelves at the edges of marine terminating glaciers, they disturb the force balance. And ocean melting, rapid ocean melting causes ground line retreat, and the ice sheets have become unstable. It's only recently in the 6th assessment report, and you'll hear about that next month, I guess, in some publications that are coming out, that the ice sheets have been fully coupled into the climate models that make those predictions. So we need to keep monitoring in the absence of reliable predictions or predictions we can have confidence with. But what was the state of play in the 1990s when CryoSat was invented? So this was the 2nd assessment report then of the IPCC. And if you look through this report, it's quite old now, and this is not to humiliate the scientists of the day. They had little information. They didn't have satellite observations. They thought that the polar regions were going to grow on average in a warming climate, simply through increased snowfall. As you warm our climate, we get more vigorous evaporation and then precipitation from the atmosphere. And in the polar regions, that falls as snow. And if we don't have ice dynamical imbalance, then the polar regions will grow. And against that backdrop, actually, lack of knowledge about how the polar regions might respond, CryoSat was proposed by Duncan, Wingham and others, and it was successful. ESA saw promise in the satellite, and it was commissioned for launch. The basic principle for that, the pitch, should we say, for that mission was really about sea ice, because the satellite altimeters that flew in those days didn't see most of the sea ice pack. So this movie shows exactly what the problem is. This is Arctic sea ice as seen by a satellite like ERS or Embisat that turns 81.5 degrees, and you miss most of the sea ice pack. And that's important because the sea ice pack is moving around the polar ocean. And if we take a look a peek inside the area that CryoSat sees, then there's lots and lots of activity there. And we can't tell people how much sea ice there is if we're not monitoring half of the sea ice cover. And we certainly can't tell anybody how it will be in the future when it retreats to beyond that circle. So we need a mission that flies simply over the poles, but we also need a mission that can detect the signals that we know are important. And some of those are the mountain glaciers, which are quite small in places like the Antarctic Peninsula here and rugged. And the conventional ocean altimeters with a footprint of 10 kilometers were just not up to this task. But also the sea ice flows. We need to be able to detect the cracks between flows, known as leads, where the ocean surface is exposed, because we measure the height of the sea ice freeboard above the ocean surface. And so we need these lead measurements every so often in order to make the sea ice freeboard and then thickness calculation. And so you need an altimeter with a fine footprint on the ground as well. So they were the two innovations for CryoSat. It had a near polar orbit, very high inclination, 92 degrees, sorry. And it had a synthetic aperture radar interferometer altimeter on board, something that hadn't been flown before on Earth. And these two things allow us to measure Earth in fine detail with the sorts of spatial scales of outlet glaciers for the polar ice sheets, ice caps around the planet, and sea ice flows in the Arctic and the Southern Oceans. So that's the basis of our measurement capability. So the mission was launched first, and that failed, and then again in 2010, and that succeeded, and it's been in space since then. This is a chart of the number of publications, the work that hopefully some of you on the call today and many others have been doing. There's now about 100 scientific papers per year based on CryoSat measurements. And the mission will continue, at least for the foreseeable future, because we have all systems nominal as far as the measurement capability and the fuel resources are concerned for a few more years. But I'll come back to that later on. So I want to give some examples of the polar science that we've been able to learn thanks to the satellite measurements from CryoSat. And I'll take you back, first of all, to the early days of pulse-limited altimetry in Antarctica. So this is perhaps one of the first iconic measurements from altimetry of the polar ice sheets. John Bamber and Bob Binchadler produced an elevation model of Antarctica, in this case, from ERS and EMBISAT data, ERS data actually in this time. 1997, so this was ERS1, and we saw for the first time the terrain, the topography, the height of the Antarctic ice sheet surface in really quite beautiful detail. And then around about the same time, Duncan produced a map of elevation change, height change for Antarctica. And this was state of the art for the day. Maybe not state of the art in terms of color scales, but state of the art in terms of measurement capability, using crossovers to track height changes over time across a very, very large area, Antarctica, that hadn't been mapped before. And the signal was more or less one of little overall change, but even that was an important result. For climate science, we needed to know whether Antarctica was growing or shrinking in order to balance the sea level budget. And the same was true for Greenland. But there was a sniff of a signal in West Antarctica, even then. Nothing much was made of it in a 3 or 4 year time record of altimeter measurements. But the next time we looked, it became clear that something was happening in the Amundsen Sea. It wasn't just us that looked. Frederic Remy and others have done similar work with ERS and EMBISAT altimetry and shown a signal of rapid thinning around the Amundsen Sea sector of West Antarctica over Pine Island and Thwaites glaciers. And then in our latest assessment, using all of the radar altimeter missions from the European Space Agency over 25 years, we see a progressive spreading of the signal of thinning over time. In the 1990s, it wasn't really quite very extensive at all. But by the end of the 2010s, 2017, in this contour, it had spread to half of the Amundsen Sea sector, at least. So within a generation, 25 years, the whole of this basin in West Antarctica had been dynamically activated. And that's a real worry. That tells us that things can happen dramatically in a lifetime. And we published this nice animation that shows the spreading of that signal over time along the tributaries of those glaciers in West Antarctica. That's Hannes Conrad's work. In Greenland, we see similar signals. This is a map of elevation change for Greenland produced by Tom Slater from CryoSat measurements, a decade of measurements, but other people, Helm produced the first one, then Mal Macmillan, Louise Sorensen, and Sebastian Simonsen, among others. And also Tom's produced this latest update now, showing the same signal: deflation around the margins of the Greenland ice sheet, hot spots around rapidly flowing outlet glaciers in the west central coast, the Jakobshavn and Isspray, and the eastern coast, Helheim and Kangerlussuaq glaciers. Greenland loses half of its ice each year by surface melting. This is a map of surface melting produced by, in this case, the RACMO regional climate model from Michiel van den Broek and colleagues. And if we difference those two signals, what's left behind is the glacier dynamical imbalance. And you can see those hot spots. They're glaciers speeding up, and they're pouring more ice into the oceans. Greenland's losing ice net today in many years in its surface alone, but with the outflow from these glaciers as well, it's a real significant contributor to sea level rise. So if we look at the two ice sheet thinning patterns together side by side, Greenland's much smaller than this in reality, but this is to allow the detail. We can see if we drop on top the ocean temperature, part of the problem, or in some cases all of the problem. This is a heat map which shows ocean temperatures above freezing in red and below freezing in blue. And in all of the areas where the glaciers have become activated, there are warm ocean currents in front of the ice sheet. This is marine ice sheet instability happening during our lifetimes. The question as to what's triggered that ocean heating still remains to be resolved, but the fact that these glaciers are speeding up and the ocean is too warm is not up for debate anymore. These two things are coupled, and they need to be properly represented in climate models. One of the other things that we've learned about is grounding lines in Antarctica in particular. So the grounding line is the junction between the bottom of a glacier and the seabed when it flows into the ocean and is below sea level. And it's a really important junction because it tells us the lateral extent of the ice sheet actually, and also gives us an early warning sign of instability, advance or retreat of this location, tells us that things aren't in a state of balance. And we can monitor this grounding line from space because of the surface expression of that tidal signal, which forces the freely floating part of the glacier system, the ice shelf, to move upwards and downwards every day. We can't see it itself because it's maybe a kilometre or two below sea level in very inhospitable location. You can't access it, but you can see the surface expression of it. And you can do that in altimetry because as the altimeter, if the altimeter returns to the same place, as the glacier thins, the grounding line migrates inland, and we can relate the two signals to one another. And Hannes Conrad has mapped, as well as Anna Hogg, the lateral extent of Antarctica's grounding line migration in this case from the satellite altimetry, which has really allowed us to study this signal of marine ice sheet instability some more in a way that we couldn't before. I'll talk about ice shelves now. Ice shelves are the floating sections, as I've said, of glaciers once they spread out into the ocean. This map that I produced in 2009 from multi-mission altimetry shows then the state of the art in maps of thickness change, a single color for each ice shelf. You can still see hot spots around the Amundsen Sea sector, ice shelves thinning more rapidly there than elsewhere. But it wasn't until we had a much more detailed look at the ice shelf thinning signal, this example produced by Sushil Adusamili last year, that we could map the coincidence of the ice shelf melting with the ocean forcing, as I showed you before with the grounded ice thinning. So these things are all coupled to one another. We have warm oceans, melting ice shelves, and accelerating glaciers. And that system, that complete system, needs to be included in an Earth system model if you want to be able to simulate the changes of the ice sheet itself in the future. You can't ignore the grounding line junction, and you can't ignore the ice shelves themselves. It's not enough to just simply have the ocean temperature changes and an offline ice sheet model. So sea ice next. Well, we've produced now lots and lots of animations, time series of sea ice thickness from CryoSat measurements. This is based upon Rachel Tilling's early work in 2015, but many others have looked at it, Robert Ricker and others at RV, Stefan Hendricks, Ron Kwok at NASA. Lots and lots of other people are interested in Arctic sea ice thickness changes for many different reasons. It's not just a climate signal, it's an obstacle to maritime activities in the Arctic Ocean. And so people need to know how thick the ice is for operational reasons as well as for climate studies. But this time series now goes for 10 years. It shows us the time variation in sea ice thickness in the Arctic during the winter months. We can't track sea ice thickness in the summer months because of the presence of melt bonds. But what we've been able to do more recently, and this is work by Isabel Lawrence, and she's managed to difference the signal from CryoSat to another altimeter mission. In this case, she used Altica, but Ron Kwok's used IceSat to get at the snow layer, which sits upon the sea ice floes. And that, if you don't know, is a really important signal for us for two reasons. It's important because it's part of our retrieval for sea ice thickness. We need to be able to measure it. But it's also really important for stability of the sea ice pack itself, because a snow layer is essentially a thermal blanket on top of the sea ice. And the thicker the snow layer on top of the sea ice, the more insulated it is from changes in air temperature. And so it has a more secure future if that snow layer is thick. So we want to be able to monitor it for two reasons: for the climate sensitivity, but also to improve our retrieval of sea ice thickness. So mountain glaciers was something that were not part of the original mission objective. CryoSat's original mission was to study simply the polar ice sheets and the sea ice pack. But we can look at them now thanks to some really quite impressive technical advances that have been made in processing the interferometric data. This has really been driven by Noel Gormelon at Edinburgh and his group, Luca Forrester, Olivier Jacob and Paul Tepes, among others. And what we can do, and they've done it very successfully in a series of case studies and projects now, is process the full width of the echo when the satellite's operating in interferometric mode to recover surface elevations beyond the satellite ground track point of closest approach, which is the normal location on the surface of the Earth where we can map height. And so this is a traditional map of Greenland's ice elevation mapped in the point of closest approach only from CryoSat data over the Petermann Glacier. And if we lay on top of it the swath process data, you can see that there's a vast improvement in the spatial density of the signal. We can pick out the full spectrum of color across the ice sheet margin. We can map the surface in far, far finer detail than we could before. And this is a really key advance in our ability to map ice sheets, ice sheet margins, ice caps and mountain glaciers, because they typically have quite rugged terrain, which is too challenging for a traditional SAR altimeter. And an interferometric altimeter measures too sparsely in space. But if you process the full swath, as was done here to map changes in height over time, now at Vatnajökull in Iceland, and lay the full swath picture on, we can see that for the first time, we can map the full extent of thickness change signals across glaciers and ice caps around the world. And I'll come back to that if I get time and look at the Earth ice mass imbalance. We've looked at icebergs as well, not part of the mission objectives. Icebergs are of interest popularly to the public. They like to hear about icebergs. You'll have seen this in the news over the Christmas period. There's a huge iceberg drifting around in the Southern Ocean called A68. It was worrying South Georgia for a period of time over the Christmas period. And lots of people got agitated and animated about whether or not it would crash into the island and destroy the marine habitat there for the ecosystem. We were able to map the thickness of the ice shelf from space using CryoSat. And that, in fact, became an important consideration because the seafloor bathymetry around the island was known. And so the thickness of the iceberg determines the limit of how close it can get to the island. In this instance, we're looking here at Anne Brackman-Folgman's work, a different iceberg, B30, which broke off from Thwaites Glacier in the mid-2000s, late 2000s. And it's been drifting around, still alive, in the Southern Ocean for 5 or 10 years. And this is the chart trajectory it's taken during its lifetime. So she's painstakingly looked for the iceberg in Sentinel-1 and MODIS satellite imagery, co-registered its location to the initial place where it broke free from Thwaites Glacier, and mapped for the first time the thickness change of the iceberg from space over time. Her paper is in the cryosphere right now in review. So if you want to take a look at it, please head over there. And I hope you like what she's done. but we managed to apply the same technique to this B868 iceberg quite quickly over Christmas to map the thickness change of the iceberg over time. And you can see here in this movie that data reproduced on top of the time-changing maps of its aerial extent. So this is a real-time monitoring system for icebergs, if you like. Subglacial lakes are a topic that lots and lots of people have become interested in over the past 10 or 15 years, thanks to their detection in satellite altimetry. In 2006, 2007, Duncan Wingham and Helen Fricker both had papers out which showed mapping of an active subglacial lake system in Antarctica, different ones, one in East Antarctica and one in West Antarctica, for the first time. And this is different to mapping the location of subglacial lakes. It's mapping activity within them, the exchange of water between networks of lakes in the ice sheet drainage system below kilometers of ice. And this is a movie made by Noel Gormelen's group, George Malchik and others, in this instance in Thwaites Glacier from CryoSat measurements, looking at height changes in the raw satellite data of the ice sheet surface that could only be caused by changes at the base of the ice sheet. This is in an area that's too slow for changes, rapid changes in ice advection. It has to be changes in the subglacial hydrological network beneath the ice sheet. And they produced this beautiful animation of that network of rivers intersected with lakes beneath the ice sheet surface, all from measurements 2 kilometers above through the thick ice. It's really quite fantastic that we can do this from space. So this is now Helen Fricker's map of Matt Siegfried and Helen Fricker's map of subglacial lakes, active subglacial lakes across all of Antarctica, many of them detected from satellite altimetry alone, and some of them only thanks to CryoSat measurements. And the first lake that people have explored, for instance, if you're interested in why people are interested in these, they're pristine habitats, the sort of habitats we might see in the solar system one day if we collect measurements elsewhere. And we need to be able to explore these cleanly. And so these are microbes collected from Lake Willans in the West Antarctic ice sheet around the Saipal Coast area, drilled into, thanks to knowledge that it was a subglacial lake, exchanging water between a hydraulic network. And these microbes are life at the base of the ice sheet, 2 kilometers from the Earth's surface, millions of years, in fact, from the Earth's surface. This is life from millions of years ago. And so if we can perfect techniques to study this sort of habitat, we can have some hope of being able to detect similar things elsewhere in the world. So lots of people are interested in altimetry for looking at the global oceans. And I won't go into too much detail here because it's not my field of expertise. But suffice to say, CryoSat measurements have become really helpful there as well. So this is a map of the marine gravity anomaly produced by Dave Samwell using CryoSat measurements. And it gives us a map of essentially the tectonic activity on the seabed, thanks to gradients in the sea surface. We can use those measurements from the ocean surface to build a complete picture of the sea level rise record over time. This is Remco Charouz's data. And we can also look at time variations in ocean topography. This is Tom Armitage's data in the Southern Ocean, looking at the CryoSat measurements to map changes in ocean currents over time. So we produced this beautiful animation which shows a composite of all of the CryoSat measurements from those different parts of the planet. You can take a look at that on the ESA website. I won't let it run now. Because I want to get on to the study that we reported last week, in fact, about Earth's ice imbalance, because it's a wonderful example of how useful CryoSat data have become in areas of climate science that we didn't anticipate them to be useful. So Earth has got lots of different parts of the cryosphere, and we looked at them all. We looked at the Antarctic ice sheet, the Greenland ice sheet, Arctic sea ice, Southern Ocean sea ice, Antarctic ice shelves, and mountain glaciers. All of the ice, it's not all of the frozen part of the world. It doesn't include snow, it doesn't include permafrost, but it's all of Earth's ice. And this study looks at the budget for how they've changed over time. And this again is a nice graphical illustration produced by Phil Eales for us to show what that ice might look like. This is New York City, taken from the International Space Station. A really beautiful image. Downtown Manhattan is about 3 kilometers wide, in case you've never been there. So the rate of ice loss from mountain glaciers is 266 gigatons per year. And that's an ice cube of this size, 10 kilometers across its base and to about 2 kilometers high. Greenland ice sheet adds another 166 gigatons per year. The Antarctic ice sheet, 111 gigatons per year. Together, these three parts of the land ice system have contributed 34 millimeters to sea level rise in our lifetimes. Floating ice, for those of you avid Twitter followers, will have learnt, has a sea level contribution. I wrote a paper about that in 2009. We haven't budgeted the sea level contribution due to floating ice. We're just interested in the land ice. But the floating ice is losing mass as well. So ice shelves have lost 284 gigatons per year. The Arctic sea ice cap has lost 329 gigatons per year. And Antarctic sea ice over this period has also diminished 40 gigatons per year. So that's 1 trillion tons of ice per year lost on planet Earth over the past 30 years. That's a 10-kilometer cube of ice every year. And that's rising as well, unfortunately. In the early 1990s, it was about 0.8 trillion tons a year. Today, it's 1.3, 60% more rapid. So this is a map of the ice loss across our planet. There isn't any part of the planet, there isn't a corner of the planet that remains untouched. All parts of the cryosphere are losing ice. Sorry, I just skipped across a couple of slides. So I want to talk about some impacts of ice loss. This is a comparison that Tom Slater has done and updated for Greenland and Antarctica. Ice losses as produced by our global assessment from IMBY, and comparing it to the IPCC assessment report predictions that were made at AR5. What we can see is that the ice losses are tracking the upper range, or the worst case scenario, and that means an extra 17 centimeters of sea level rise by the end of the century, over and above the mid-range, which is the normal thing that's reported. And is that important? Well, this is New York City, when Hurricane Sandy struck, lasted for 2 or 3 days, as hurricanes tend to, and caused torrential downpours, high sea stands, and storm surges, which eventually led to flooding in the city after a certain period of time. 17,000 properties were destroyed. 50 square kilometers of land was underwater, and 46 people died as a consequence of this flood. And if you look at the sea level curve, battery on the Hudson River, you can see that spike. It's a huge storm surge on the 22nd of October in 2012. And that's an unusual event for sure. That's something that hasn't happened in that year at all, and in other years since. But if we push mean sea level up by this extra 17 centimeters on top of the AR5, you can see that kind of flooding in 70 years' time will happen most years during high storms and high tides. And that's something that every coastal city will need to plan for. In the UK, where I live, Yorkshire has a coastline that isn't just flooding, it's eroding. This is the Humber Estuary in the UK. And a huge number of people are exposed to sea level rise and floods in this part of our country, and we depend upon it because it's a port, and we can't bring goods into coastlines that are retreating away and have to be shifted as sea levels change. And so every country has its weak spots, and the UK is not immune, and your country won't be either. And if you look at the global population that's exposed to sea level rise, it's estimated that about 250 million people already today are in a situation of having to cope with annual flooding. By the end of the century, that's set to rise to about 300 to 350 million, depending on how the ice sheets continue to respond to the ocean forcing and atmospheric forcing. So for every centimeter of sea level rise, you can expect 3 million or so people to be displaced by the end of this century. New York City is already making plans to reclaim land around Lower Manhattan. That's a $10 billion scheme. San Francisco already did the reclaiming of land. The historic shoreline is well beyond the current shoreline if you've been down to the embankment, which floods periodically. San Francisco is planning to defend its airport because it's at 5 meters above sea level, and that's exposed to storm flooding. So this is a reality for most parts of the planet. And I just want to finish on 2 or 3 slides, I know I've overrun, about whether or not we can do anything as scientists to help. There are lots of things we can do as individuals to help. You can vote in governments that will do something about it, right? But as scientists, there's lots of work still to be done. We can't just rely upon the capability that we have today to monitor these changes. Here's a good example. We need to fix models. This is a model simulation of the Amazon Sea sector over the next 200 or 300 years and how it might respond to climate warming in the future and give up some more of its ice. How have models performed over time? This is some work I did with Sophie Nowicki in 2017. We looked at the IPCC's predictions for sea level rise from Antarctica and Greenland in the first assessment report, and the second assessment report, and the third assessment report. It was assumed that Antarctica would grow and Greenland would shrink, but they would offset one another. And then by the time of the fourth assessment report, there was a recognition that ice dynamics might start to be playing a role. And then ultimately in the fifth assessment report, it was recognized that both ice sheets would actually melt in a warming climate. And they're the observations. And so the models have certainly improved over time, but they're not perfect. So when we look back at that projection that I showed you for sea level rise, this is the satellite observations compared to the IPCC's predictions. We're not tracking the mid-range scenario, we're tracking the upper scenario. The question is can we get back onto a better trajectory in the future? And our knowledge of that will come from studying ice. It's the first part of the climate system to respond to climate warming. And so studying the recovery of the ice in the future could be something that we could positively contribute towards society. But do we have the tools? And that's not clear to me, because in my lifetime, we've had a steady train of satellite measurements, altimetry. We've had ERS-1, ERS-2, ENVISAT, ICESat-1, CryoSat, and ICESat-2. But we don't have a future satellite altimeter mission for the polar regions. The European Space Agency and the European Commission are developing a candidate mission, Crystal. It's going to be subject to a selection process towards the end of this year. It might not get selected. It's not the prime candidate mission right now, even of the ones that are being considered. There isn't enough money in the Copernicus space program to pay for all of the missions. This mission might not get selected by the end of the year. But even if it does get selected, there's going to be a gap between those measurements of about 5 years is my guess, and I'll buy you a beer if I'm wrong. There'll be a gap. What can we do to bridge that gap? We could extend the lifetime of CryoSat-2. We're trying to do that. It's unlikely. There's a fuel leak on the mission. We could extend the lifetime of ICESat-2. That's out of my hands. Lasers are expensive items to operate. That's all I know. We could accelerate the build of Crystal, or actually at least make sure it gets commissioned. Again, that's outside of my hands, but I'll do my best to persuade people that that's a good thing to do. We could shift one of the multiple ocean altimeters that we have ready to be launched into space. Sentinel-3C and 3D have not been launched into space yet. We could launch one of those into a near polar orbit to support climate science. We could launch a bunch of CubeSats. Some people think they're confetti, but we could launch a bunch of these into space. This is Busek Technologies. They have a CubeSat altimeter. Or we could fly an airborne monitoring program. If we don't want to see a gap in our polar altimetry capability, we have to do one of these things. And somebody has to take a decision as which one to back. I hope you'll try and support them. So I just want to summarize. CryoSat is 10 years in space and counting. There are now 100 papers per year, which is great, I think. I'm really pleased with all of the work that everybody's doing. It's exceeded its mission objectives to track sea ice on the ice sheets. It's now monitoring grounding lines, icebergs, ice shelves, mountain glaciers, subglacial lakes, oceans, rivers, and much, much more than that. Its capability is extended beyond its original technical objectives with swath interferometry, but also fully focused SAR over sea ice. The data are integral to assessments of global ice imbalance. I showed one of those. Climate model skill, I showed some of that. Climate trajectories, I showed some of that. And also operational services. I didn't go into too much detail, but the measurements are included in sea ice forecasts. Our challenge is to bridge the imminent gap in polar altimetry, and I hope that you'll lend us your support. With that, I'll end. Thank you.
Thank you very much, Andy, for this beautiful lecture with extraordinary animations. I would love to be able to do the same, but I know I'm not able. So it was really wonderful. So now we have time for questions. So there are two possibilities for the participant. Either they write their question in the chat or they raise their hand, and Willie will let them talk. So do we have... okay, I don't see... oh, there are already two hands raised. So
I can't see any of the chat, so somebody will have to ask me the questions.
Yes. So Willie, can you allow the participants to speak?
You say which one you would like to go first, Annie.
But I don't see. I don't see. I'm sorry. I don't see the names of the people who want to speak.
So this is Mark Drinkwater, Annie.
Okay. So, yes. Okay.
I had a question to Andy because it might help to start the ball rolling. And Andy's mentioned about the possibility of a successor, but there are many things that we could still do to advance data processing for CryoSat. And there's things like fully focused SAR and product advancements that go beyond even where we are today. Could you say something about where you think the main advances are that remain to be made with the existing CryoSat data and the capabilities that we have today? That would be good. Thanks.
Thank you, Mark. So without a shadow of doubt, the one part of the climate system that we know very little about is sea ice in the Southern Ocean. And the reason we know little about that is because it's a challenge for satellite altimetry. We can map the extent. It hasn't changed a great deal over time, but we can't really map the thickness because we have very little knowledge of the thickness of the snow layer on top of the sea ice flows in the Southern Hemisphere. It snows much more down there than in the Arctic. There's less melting than there is in the Arctic. And it's a different evolution seasonally. And it's a challenge for altimeters, either laser or radar altimeters. The great thing that we've got going right now is the Cryo to Ice campaign, which is flying CryoSat in a semi-tandem orbit with IceSat. And so we hope to be able to crack this particular nut in the coming years so that we can produce today, but also backwards in time, estimates of sea ice thickness in the Southern Hemisphere. And that's really important for climate science because it's widely accepted that a lot of the heat that Earth has absorbed in the past 20 or 30 years is being stored in the Southern Ocean at depth. And the question as to whether or not that's impacting the sea ice thickness over time becomes a pertinent one. In terms of technical advances, as you've seen, we have some really quite beautiful imagery for polar ice sheets now. I think that if the advances in our measurement capability for the polar ice sheets will be incremental, but not for mountain glaciers and not for outlet glaciers, in particular in Greenland, which are quite challenging, and not for ice caps, and also not for the complicated parts of the sea ice pack in the ice marginal zone where it's quite thin. And then finally, in the Arctic, I would say anybody working on the signals from any flavor of altimeter during the summer months will see profit in the future because we still know very little about that.
There is another question in the chat. I don't know, Andy, if you can see it or not.
I can't, no.
You cannot. Okay, so the question is, what is the effect of loss of ice to the Africa region?
Loss of ice to the Africa region, right. Okay, so for the world as a whole, ice melting causes sea level rise. And if there's a coastline anywhere, it will be affected. The redistribution of mass on the planet as a consequence of melting from either Greenland or Antarctica is curious if you don't know about it. ice losses from Greenland preferentially affect the southern hemisphere, and ice losses from Antarctica preferentially affect the northern hemisphere because there's a rebound effect of the bedrock below it. But on balance, it turns out that Antarctica and Greenland are giving up a similar amount of ice to the oceans as one another, and so that effect is offset to some extent. And so the sea level rise will affect Africa as well as any other continent in the mean. So that average of an extra 17 centimeters is for planet Earth on average. Some places will have a bit more, some places will have a bit less. The other effects of ice melting are the disturbance of hydrological cycles. The glacier systems around the planet are real water towers for billions of people. That's not such a problem for Africa. Not many people rely upon mountain glaciers for water resources in Africa. There are some, in particular in southern Africa. And the main other effect is disturbance to ocean currents, and that's going to affect everywhere on the planet, but over a longer time scale.
Okay, the next question in the chat is from Jérôme Benveniste. The question is, what are your plans for the next scientific challenge in the next 5 years?
So the next scientific challenge is to secure, not for me, but for the next generation of scientists, the next satellite altimeter mission for the polar regions. I've been trying for, I would say now, 5 years to secure this mission, and it isn't secured just yet. There has been progress. I think it will take another 5 years to make sure this capability is guaranteed. Bear in mind that I mean, my career has been built upon the efforts that were made in the 1970s and the 1980s by space scientists to persuade the space agencies to invest in Earth observation rather than interplanetary observations alone. And that message was heard, but it takes decades. It takes decades to implement, partly because of technology, but actually really because of budgets and programs and funding opportunities. We could rebuild CryoSat in 3 years, and that has remained the case for the past 5 to 10 years. CryoSat costs the European citizen 1 cent each per year. This is not an expensive thing.
Okay, so thank you. The next question is it's more a comment. You have not shown a comparison to air temperature. So the question, I understand the question, is there a correlation with ice loss and increase in Earth? I don't know if it is Earth or ocean temperature. So can you comment on that?
So I did show a comparison to air temperature, and I also showed a comparison to ocean temperature. I showed the maps of Antarctica and Greenland thinning surrounded by ocean temperature changes. And I also showed Greenland melting driven by an atmospheric model only and as observed by the satellite altimeter. And the difference is the ice dynamical imbalance. Air temperature changes are driving the melting at the Greenland ice sheet, and we're actually quite good at modeling that now.
Okay, so I don't know if there are other questions in the chat. If not, I have 2 questions for you. The first question is about mountain glaciers. You said that you are able to quantify ice mass loss from glaciers, and you showed example in northern Greenland and Iceland. But could you do that globally? We have now, as you said, we have 10 years of CryoSat, so it would be nice to have a 10-year record of global glaciers mass loss. Is that planned? Is there a project?
There is a project, and it's already delivered results. And so in our assessment that we reported last week, that includes some CryoSat measurements around global glacier systems produced by Paul Tepes and Olivier Jacob. From Edinburgh, and CryoSat doesn't see every glacier on Earth. There are 200,000 and counting. But when we look at the number of glaciers that are monitored with ground instruments, it's 50 since the last century. And so anything above that is a bonus. CryoSat sees some of the 200,000, but not all of
Okay,
them.
not all. Okay, it's a pity because it would increase the temporal resolution compared to in situ measurements for glaciers.
Yeah. I mean,
So,
it's work in progress. It's work in
okay.
progress, and it's a challenge because altimeters, as you know, Annie, don't like rugged terrain.
Yes. Okay. So, if I may, I would like to ask you another question. You talk about these subglacial lakes in Antarctica, which is very interesting. And so my question is about the microbe that people have collected. Do they see some difference with what we know on microbiological life on Earth, on land? Can you comment on that?
Well, I'm not a biologist, and so I don't know the
Yes.
details of what's been found. But what I do know is that the interconnection and what's now known as activity within subglacial lakes was a surprise. People thought that subglacial lakes were isolated systems. The classic example is Lake Vostok.
Mm-hmm.
And the assumption was that this would be a pristine environment with no disturbance for 350 million years, or whatever the time period it is since that lake water was last exposed to the atmosphere. But actually the activity, the exchange of water between these lakes tells us otherwise. We can't expect a lake that's downstream of another system to have its own unique environment. They'll all be interconnected. And so you have to move further and further upstream, up the hydrological network, to get to this Goldilocks lake, where we are looking at unique changes that have not been disturbed for millennia. I think that's what we've learned. It's harder than we'd originally thought. These lakes that are at the edge of the ice sheet, they're basically the downstream part of a network, and so anything that occurred elsewhere will have eventually passed through them.
Okay, so I don't know if there's some other questions. If not, maybe one. There is a comment from Chris Rapley. So the comment is returning to the CryoSat crystal gap. Why do you think it has been so hard to gain support?
Oh, we do have support, actually. And so if you ask anybody in the agencies involved, in particular in Crystal, that's the European Space Agency and the European Commission's Copernicus program, they all support the mission. But it's a question of priorities. The budget and the envelope budget for the next Copernicus program has to pay for 6 satellites right now, because 6 were nominated by the Space Agency as high priority candidate missions. And that becomes expensive. And also part of the reason that the Space Agency exists is to stimulate national aerospace sectors. And there isn't a particular enthusiasm to just build carbon copies of technology from the previous generation. The heritage is important in space, but innovation is as well. And so the budget can't easily be brought down. The costs always go up when it comes to space agency activities. That's a shame, but that's something that the taxpayer has to be persuaded is in their interest to invest in. And that's why it's taken so long. I mean, the other part of the problem, Chris, is the success of CryoSat. I forgot to tell people it's 3 times its nominal lifetime. It was built to last for 3.5 years, and it's now in its 11th year. And so the success of the mission is part of the problem. While ever it's flying around in space doing wonderful things, there's a tendency for people to forget that it might not fly in space forever.
It's the same for almost all altimetry missions, by the way.
It's the same for all altimetry missions, but we have a dozen surveying Earth's oceans today. Mm-hmm. And we're soon to have none surveying the polar regions.
Yeah, yes.
And I mean, of course, I'm partial because I'm a polar scientist, but I hope I've convinced in my presentation that the polar regions affect everybody on the Earth.
Yes, sure. Okay, so if there are no more questions, we will close the session. So Andy, thanks again for this beautiful lecture. I am sure all participants appreciate it very much. And before closing, I would like to remind the participants next week rendezvous. This will be a talk about the SMOS mission by Yann Kerr from CESBio in France. And he will talk about soil moisture and sea surface salinity. So good evening or bye-bye to all of you, and see you next week. And thanks again to Andy.
Thank you.
Bye-bye.
Bye.
Thank you. Bye.